Hello, I'm Dan KINZER, COO, CTO, and co-founder of Navitas Semiconductor. I'm here to tell you today about how Navitas will use gallium nitride to electrify the world with a new energy, with higher efficiency, and with sustainability to help solve our world's climate problems. Before we do that, I'd like to introduce a video clip to help you understand that a little bit better. The enabling force behind all this change is gallium nitride, a compound wide bandgap semiconductor combining gallium and nitrogen, gallium being a common element found in the mining of aluminum and other metals, nitrogen the most common element in the Earth's atmosphere. Put those two together and you get a material that has 10 times higher electric field capability than silicon and very high mobility, which leads to 20 times faster switching, 3 times reductions in size and weight, 3 times higher power density, and 3 times faster charging for your devices, while saving 40% of the energy that's lost in the system and lowering the system cost by 20%. Gallium nitride is not new to the semiconductor community. And in fact, my CEO, Gene Sheridan, and I started working on gallium nitride almost 20 years ago. But there were a lot of hurdles in the path of gallium nitride getting to the market, and Navitas has overcome those key hurdles. Those include manufacturability, reliability, complexity, and cost. In earlier days of manufacturing GaN, the yields were not so good. There were material challenges. But today, our yields are greater than 90% and comparable to silicon devices that are used in the field. In reliability, initial efforts had trouble, but we are now fully qualified with over 1 billion device hours tested and 25 million units shipped without failures. As far as complexity goes, it was difficult to drive early GaN solutions. In our case, we've integrated the drive, making it very easy to use our solution. And as far as cost goes, the factories have now ramped up in their capacity, and we've been able to take advantage of volume integration and a leading manufacturing partner to bring our costs to a very acceptable level. GaN devices switch incredibly fast, and because of that, it is extremely important to control the gate voltage very precisely. With silicon devices, you often have a driver which is included in the system controller, and you have a power device in a separate discrete package. In between, you have board-level parasitics, inductors, resistors, that affect the switching performance of the device and slow it down. The speed of silicon devices is much slower. They typically run at less than 100 kilohertz, and because of that, you get a low power density. GaN discretes can operate much faster, but they are also limited by those parasitics on the board, and even have additional complexity in order to try to deal with the very low threshold of a typical GaN technology, or even more difficult, some GaN switches that, rather than being normally off, are normally on and have to be controlled by another switch connected in series to turn off the device. Those are capable of operating a little bit higher in frequency and achieve slightly higher density. On the other hand, with Navitas, with our GaN power ICs, with our lateral device, we can integrate a number of different functions. Particularly, the drive can be right on the same chip and deliver a drive solution with precise control over the gate voltage with no parasitics in between the driver and the power switch. And in addition to that, we can add other components that will add elements of control and protection to the device. When you do that, we are capable of switching up to 2 megahertz or higher and dramatically reduce the size of the solution. From the very beginning of our company, we realized that reliability was critical to be successful with these gallium nitride products. So we started with integration. We put the driver on the same chip. In that way, the gate voltage can be precisely controlled, the switching waveforms can be precisely controlled, there's no inductance, there's no ringing, and we added extra features such as undervoltage lockout, electrostatic discharge protection, DVDT control. And with all of that, we get layout flexibility and simplicity for the user. When we do that, you can see from these waveforms the current is ramping up, and with a discrete device, you see an exposed gate that can lead to faulty switching, and you can see ringing and glitching in the waveform. Whereas on the right side, you can see a nice clean current ramping up to a higher level and still having clean square wave switching on the drain. In addition to that, we've built in lots of margin for the high voltage capability of this device. This is a 650 volt rated device. However, we allow transients up to 800 volts. And we allow operation, for example, in flyback circuits with spikes going all the way up to 650 volts. And that can be done continuously in every cycle without danger to the device. All of that leads to a great result of having shipped more than 25 million parts into the field with no failures, with a fit rate less than 1. And we now have equivalent device hours in the field of around 75 billion and equivalent device hours tested of almost 6 billion. Navitas is full of leaders in power semiconductors and power electronics, with many, many years of experience and a demonstrated track record of invention. We have invented multiple aspects of GaN power ICs. We have also advanced the state-of-the-art in GaN power devices, as well as high-frequency packaging and high-frequency power electronic systems. In addition to that, we have developed a process design kit, or PDK, which includes advanced devices, multiple advanced devices, multiple advanced circuits, highly accurate and capable models for simulation of those integrated circuits, and I have a fully capable characterization platform. All of this leading to a design environment that our engineers can use to design advanced power integrated circuits that are leading in the state of the art. Since the founding of Navitas, a major motivating force has been to save energy, reduce fossil fuel consumption, and reduce CO2 emissions. Every GaNFast Power IC shipped saves 4 kilograms of CO2 by our analysis. This is 4 to 10 times lower than silicon due to the reduced number of process steps and the much smaller chip, which leads to many more chips per wafer. In applications like chargers and adapters, the charger itself will have a 28% lower CO2 footprint due to both the saving of energy and the reduced material content in these high-density, high-efficiency chargers and adapters. In the area of electric vehicles, by charging faster and by reducing the size and weight of the power electronics and the battery in the system, we can accelerate the adoption of electric vehicles by 3 years using gallium nitride. And this will save 20% per year of road sector emissions by the year 2050. Overall, gallium nitride in power electronic applications can address 2.6 gigatons per year by that time, which is approximately 10% of the savings that we need to get to carbon neutral. This graph shows the future range of applicability of different power semiconductor technologies. In the low voltage end and low power end, silicon will continue to be the dominant technology. And at the very high power end, above 1200 volts and 100 kilowatts, silicon carbide will displace silicon IGBTs and other existing silicon technologies. In the middle, and over a wide range from 80 to 1000 volts and from 10 watts up to 100 kilowatts, GaN will be a technology of choice, covering many applications. Adapters at the low power end, but consumer electronics at higher powers, as well as LED lighting, game systems, solar microinverters, base stations, servers, data centers, all the way up to electric vehicles, as we described earlier. Navitas gallium nitride power ICs will recharge and bring new life to the power semiconductor market. Last year, gallium nitride represented less than 1% of a $9 billion addressable TAM. That TAM will grow at a 6% annual rate, but the penetration of gallium nitride into that market will grow at over 100% annual growth rate, bringing it to a $2.1 billion market opportunity in 2026. That $2.1 billion breaks down in multiple segments, starting with the mobile applications, adapters, chargers, adding on consumer, enterprise, data such as data centers and communications, renewable energy, particularly solar, and electric vehicles and e-mobility, adding up to a total of $2.1 billion. The revolution in chargers and adapters is well underway, with over 140 customer projects in production, great new products that are 3 times smaller and lighter and cost less, products such as the one pictured here, which can deliver 3 outputs to replace 3 chargers, and many other applications that are pictured for major manufacturers and OEMs like Lenovo, Dell, NVIDIA, Oppo, Xiaomi, and many others at various power levels from 30 watts up to 150 watts. All of this adds up to over 25 million parts shipped and 0 field returns. GaN power ICs can deliver amazing size reductions. Pictured on this slide are 2 adapters. The one on the left, a fairly typical 45 watt GaN adapter from Samsung. On the right, a very advanced GaN power IC powered adapter from Oppo. If you look at the system on the left, you have about 0.5 watts per cubic centimeter. The system on the right, 3 times as much, 1.5 watts per cubic centimeter. The system on the left operates at pretty much the same frequency that silicon adapters have been operating for quite a few years at 65 kilohertz. As a result, the transformer inside and the capacitors inside are pretty much the same size as they have always been. The system on the right, however, uses 400 kilohertz, which is over 6 times faster switching, and as a result, it can go to advanced planar transformer technology. It can eliminate all of the electrolytic capacitors in the system and shrink down to this amazingly thin form factor. This is enabled by Navitas GaN power ICs. The next class of applications, which is adopting GaN power ICs in a big way, is consumer electronics. Systems like ultra-thin LED TVs, game systems, all-in-one PCs, and smart home all need higher power in smaller size. And GaN power ICs make that possible. We increase the power density of systems across the board while saving up to 40% of the energy. As you can see pictured here, we can shrink a 150 watt adapter dramatically. 65% smaller, thinner, and lighter. So we solve that problem that consumers demand for more power and smaller form factors. And we've already been awarded applications in smart TVs, all-in-one PCs, and all in all, these applications represent a $2 billion opportunity for gallium nitride power ICs over the next several years. 44% of the cost of a typical data center relate to power electronics, cooling equipment, and electricity consumption. We estimate GaN power ICs can reduce electricity use by up to 10%, and across all data centers, that would add up to more than 15 terawatt hours or $1.9 billion in annual electricity costs. One example of how that will be done is pictured below with a silicon power supply at 2.2 watts per cc, delivering 3.2 kilowatts. With GaN, that same 3.2 kilowatts can be delivered at twice the power density, 4.4 watts per cc, and a 38% reduction in energy lost. If you look at the total system going from the grid to the processor, GaN can increase the efficiency from 75% to 84% by being applied in both the AC to DC converter on the front end and the 48 to low voltage converter that follows that. We are already engaged with top data center suppliers, and many of these are the same customers that we supply mobile and consumer markets. 13 million servers with greater than $75 of GaN content can add up to an over $1 billion opportunity for gallium nitride. GaN ICs can significantly reduce the payback time for solar installations in the home. We can do that by lowering the inverter cost by about 25%, moving from silicon to GaN, as well as reducing the power loss, the power dissipation, by over 40%, from 158 watts down to 94 watts. GaNFast microinverters are a major new opportunity in solar, as well as GaNFast energy storage systems. So this opportunity is an over $500 million opportunity just with one major solar supplier. So the total residential solar opportunity is over $1 billion per year. And the payback for the user can be improved by 10% or more. Let's hear from Enphase Energy on gallium nitride in solar.
After 25 years of development, it's the end of the road for silicon MOSFETs. Enphase has considered both silicon carbide and gallium nitride technology for adoption in microinverter products. Silicon carbide technology can offer a 2x switching frequency advantage over silicon at a similar cost. However, gallium nitride offers more than a 10-fold switching frequency and system cost advantages, making it particularly attractive for the Enphase microinverter application. Enphase has had a relationship with Navitas since 2015. We appreciate the focus on and support of the Enphase microinverter roadmap, with gallium nitride at its core.
We believe that GaN power ICs will drive significantly faster adoption rates for electric vehicles. The adoption rate is limited today because charging times are long, the range is not enough, and the battery is expensive. GaN power ICs can address all of these points. The opportunity for GaN is significant in the traction, the onboard charger, and the DC to DC converter. GaN can deliver much faster charging times, as much as 60% faster, as much as 70% reduction of losses in the inverter, and by doing so, a 5% reduction in the battery cost or a 5% increase in the range. All of this leads to a very large opportunity in electric vehicles, and in one customer alone, Navitas is working on a $400 million opportunity, and across the entire market, there is a multiple billion-dollar opportunity. And now, from Brusa High Power, supplier to BMW, VW, and Porsche, let's hear about GaN power ICs in EV applications.
Brusa High Power products are onboard charger and DC-DC converters with applications in on and off highway market segments. The efficiency, power density, and overall size and cost of our products are driven by the performance of the power semiconductors. Our current product lineup is based on a combination of classical silicon IGBTs and silicon carbide wide bandgap power semiconductors. Brusa High Power is convinced that gallium nitride, or GaN, will enable us to further improve our products. The main advantage of Navitas GaN power ICs are simplicity of driving, high-speed switching performance, and increased reliability and a compact form factor.
It's been an exciting ride in Navitas from the very beginning. When we built our first prototype back in 2014 of the world's first GaN power ICs, followed by the world's most advanced half-bridge power IC a year later, then followed by application examples of 25 watt and 150 watt adapters, then up to 3.2 kilowatts for a data center prototype. More and more patents generated throughout this. The introduction of our product in 2018 and the beginning of adoption in consumer adapters, followed by even more advanced prototypes, extending the power of adapters up to 300 watts, crossing the mark of 100 patents, and then high volume adoption by major OEM in-box applications. And now, with over 25 million units shipped and with 0 failures, we are ready to take on new markets, new customers, and to see GaN adopted across the board in major power electronic applications and really address that market expansion opportunity that we're talking about of a new $13 billion market for GaN. Come join the GaN generation and Team Navitas. Whether you are one of our power electronics partners, one of our design houses, customers, universities, manufacturing partner, whether you're just a consumer buying power electronics, an investor, help us to advance gallium nitride, improve the environment, and make a better world for all of us.